We have just learned about how to sample uniformly a point on a mesh light, right? We select a triangle and then we select a point on the triangle. Okay, so the probability of selecting this point x on the triangle is equal to, on the mesh, let's say, is equal to 1 over a. Okay, so a is the, what is this? A is the area of the mesh. So the probability of selecting this point is 1 over a, uniform, and a is the total area of the mesh, the sum of all the triangles. Now, however, note that in ray tracing, we are really concerned, what we are trying to do is we are trying to find PW. Okay, so in our system, we are trying to choose, we are choosing directions randomly. And in the Monte Carlo formulation, in Monte Carlo integration, remember what we are doing was we compute L XWI, we have the BRDF term XWIWO, right? We have the cos theta term, and we divide this by PW. So actually the probability of selecting this direction is important. But what we have done is we have found a way to uniformly sample a point on the object. Now we must convert that to the probability of selecting this direction, okay? Because we need it here. Now, the way to deal with this is, first we must remember that the relationship between the solid angle, the differential solid angle, and the differential area. So this relationship was equal to the following. dW is equal to dA cos theta r square. Okay? So what is this? Basically we have a point. We put a hemisphere around this point. Okay, let's say you have an area. Okay, so let's say this is your area, dA. This is the normal of your area. And you are trying to compute the solid angle of this shape as seen from this point. Okay, so this is the direction of projection. Okay, so theta here is actually this theta, right? So this is the relationship between the differential area and the differential solid angle. So this is this being dW, and this is dA. Okay, so from this relationship we can convert the area probability to solid angle probability. Now I would like to just, we have actually talked about this in our previous lectures, but I would like to very simply explain this in a very simple way. Let's say we have something, a relationship like that. dW is 2dA. Okay, just as an example, let's say we had something like this. Okay, of course the relationship is not 2, it is this. But let's say it was like that. What does it mean? It means that, so if this is dA, okay, if this is dA, then this is dW, right? So dA, 2dA makes dW. Okay, so let's say this is also dA, 2dA makes dW. Then, if the probability of selecting x, okay, if the probability of selecting x here was, let's say, if the probability of selecting x at that point is, let's call it c, okay? Then the probability of selecting w here is going to be 1 over 2c, okay? So why do we have, I'm sorry, the probability of selecting this is going to be c over 2, okay? So why do we have that? Because we now have a larger, so this transformation, remember the Jacobian stuff from the previous video, this transformation is stretching the dA by 2 to obtain dW. So we have a larger now region, and therefore the probability goes down by the scaling factor here. So if you are scaling by 2, the probability goes down by 2. Okay, so now here we are scaling by cos theta r square. So what we must do is the probability of selecting W is equal to probability of selecting A or selecting X, okay? And we divide it by the scaling factor being cos theta r square, okay? So from here, the probability of W of this direction is px r square divided by cos theta. Okay, what is px? Px is equal to 1 over a. Okay, so px is 1 over a. Remember the area of the mesh. Area of the mesh. It is constant, right? So pw is equal to r square divided by a cos theta. Okay, so once we select the point on the mesh, in Monte Carlo formulation, we are going to write in the denominator pw, right? So we have the L stuff, F stuff, cos theta here, then cos theta I. We will be dividing that with this pw, and this is what this pw is going to be.